There is one topic that we haven't covered last week and we haven't covered yet this week. What happens when we have repeated eigenvalues? So let's look at an example. We have the identity matrix and we want to find the eigenpairs. The determinant of I minus lambda I equal to 0 requires lambda equals to 1. So there is only one eigenvalue. It's a 3x3 matrix with only one eigenvalue. Is it a problem? Well, in some senses, yes, because everything we have computed up to now requires 3 different eigenvalues. But if we keep going and we want to compute the eigenvectors, we retrieve that I minus lambda I times xi equal to 0 is 0 times xi equal to 0. So any vector in R3 is an eigenvector of the identity matrix. That means that any 3 linearly independent eigenvectors can be used as eigenpairs. So any xi1, xi2, xi3 such that they are linearly independent can be used to compute the matrix exponential of I, can be used to to write the solution of x prime equals ix. I mean, there's clearly one nicer solution, but any 3 linearly independent vector can be used in this context. So even though the identity matrix has only one eigenvalue, it still has 3 linearly independent eigenvectors. They're not uniquely defined, but they weren't uniquely defined anyway in all other cases. In this case, there's just more freedom to choose them. We are not only able to scale it by a constant, but also to choose how to pick these 3 vectors. But we still have 3 vectors. So in this case, using it in the context of ODEs, linear ODE systems, we're still good. We can think of the identity as the transformation that takes v1 to v1 and v2 to v2 for any v1 and v2. So let's look at another example. This is a 2x2 matrix, 1 minus 1, 1, 3. And we compute the eigenvalues, and we find only one eigenvalue, lambda equals to 2. Is this a problem? Well, if it's the same situation as the identity matrix, it's no problem. But it turns out that it's not. We still find one solution to the eigenvector problem. So if we plug a minus 2i, xi equals to 0, we still find xi has to have the form 1 minus 1 or any multiple thereof. So A is a 2x2 matrix with only one eigenvalue, and associated to this eigenvalue, there's only one eigenvector. This breaks our structure. We are not able to solve it in the same way as we have solved everything else. So how do we do in this case? Well, first of all, let's look at how A works as a transform from R2 to R2. What we find is that only one eigenvector is stretched. Everything else is moved around. Everything else is squished towards this eigenvector. And in such a way that there is no demarcation that goes in the other direction, no second option, no second eigenvector. This is a bit weird. Let's try to see if we can solve ODEs with repeated eigenvalues also in the case in which it's not similar to the identity matrix. So when we solve ODEs with repeated eigenvalues, the first case is the identity matrix case. So A, square matrix of size n, has an eigenvalue of multiplicity m. That means an eigenvalue that comes in the characteristic equation as a solution of order m. But even if lambda, the eigenvalue, has multiplicity m, it is connected to m linearly independent eigenvectors. In this case, to solve ODEs, we don't have a problem. We can proceed as usual. If we have x prime equals the identity matrix times x, we can choose the vectors 1, 0, 0, 0, 1, 0, 0, 0, 1, so the element vectors. We can use them and write our solution as a sum of these eigenvectors that we have chosen with a bit more freedom than usual times the exponential of t times some constant. We can still do the same process as usual. But what happens if lambda is its multiplicity m, but we have less than m linearly independent eigenvectors? This is a bit more of a problem. So let's study the special example that we just started with. We have A that is 1 minus 1, 1, 3, and it has only one eigenvector. One eigenvalue, one eigenvector. So the first solution, the first fundamental solution, we know. We have the first eigenvector, 1 minus 1, exponential of the only eigenvalue, 2t. There is no second solution of this form. But if we remember second order ODEs, when the characteristic equation had repeated roots, the second fundamental solution that we wanted was of the form t times exponential of rt, where r was the solution of the characteristic equation. So in this case, we want to try as second solution of this linear system of ODEs, we want to find t times a vector times exponential of lambda 1t, where we have freedom in the choice of the eigenvector to fit unknown parameters. So x2 has t times xi times exponential of lambda 1t. x2 prime would have the form xi times exponential of lambda 1t plus t lambda 1 xi exponential of lambda 1t. If we plug it in, we have that x2 prime is equal to ax for all t. So we can simplify because we can take e lambda 1t away. And then we have to match element by element where we see the different powers of t. So for power of t equal to 0, we have xi equal a xi. And for power of t equal to 1, we have lambda 1 xi equal to 0. That gives us xi equal to 0. This is not enough. This choice gives us something to go on, but is not flexible enough to allow us to find a solution. So let's try instead a sum of two elements, in which the first is a vector times exponential of lambda 1t, and the second is a vector times t times exponential of lambda 1t. We take the derivative of this. The derivative of the first element is lambda 1 xi exponential of lambda 1t, and then the second block is what we computed already, xi exponential of lambda 1t plus xi t lambda 1 exponential of lambda 1t. And we plug it in our ODE. So we have a block of three elements that is the derivative of the guess we just made equals the matrix A times the guess we just made. We can simplify away the exponential of lambda 1t because it appears everywhere. And as before, we match by powers of t. So t does not appear in the first two elements, nor in a times eta. So we have lambda 1 eta plus xi equals a eta. And t appears in xi t lambda 1 equals a xi t. We don't consider t anymore, so we have xi lambda 1 equals a xi. So this second one tells us that xi is the eigenvector, the only eigenvector we have. And eta solves a minus lambda I multiplied by eta equals to xi. So it's something that has a bit of the form of the eigenvector format, but on the right hand side, instead of 0, we have the previous eigenvector. Or we can rewrite it as a minus lambda I squared times eta is equal to 0. In this case, we call eta the generalized eigenvector. It solves something that is a bit more general than the usual eigenvector formulation. So we have found a non-zero solution of our problem. So let's check what it solves in the specific case we're looking at. Here we have a that is 1 minus 1, 1, 3, minus 2i, 2 being the eigenvalue, multiplied by eta equals the eigenvector, 1 minus 1. So we solve things, And we notice that it simplifies to -1 minus 1, 1 times eta equals 1 minus 1. Notice how the determinant of 1 minus 1 minus 1, 1, 1 is equal to 0. That means that we're solving a linear system in which our matrix representation is not invertible. So we might not have a solution, but in this case it has, because you notice how also in the matrix formulation we have that the second line is equal to the first line multiplied by -1, and in our right hand side, in the vector 1 minus 1, we have the same format. So this rule equation has the situation that the second line of the equation is equal to the first line multiplied by -1. So we still are able to solve it. We have that eta is equal to a in the first element and minus a minus 1 for any value, real value of a. So eta can be 0 and -1, but also 3 and -4. So we have the solution that x2, the second solution for our problem, has a unique solution in the sense that we can find eta and xi such that eta times exponential of lambda 1t plus xi times t times exponential of lambda 1t is a solution. So we can write the general solution, the full solution of our ODE system depending on C1 and C2. So we have C1 xi exponential of lambda 1t plus C2 multiplied by the whole block eta exponential of lambda 1t plus xi t exponential of lambda 1t. This is true in general. In cases in which your multiplicity is higher, what you have to do is having even more terms in the block depending on xi. So we would have terms with higher multiplicity of t. So eta 2 exponential of lambda 1t plus eta 1 t squared. You would go up to t squared. I might write it down in order for it to be more clear. In the example, if we want to write it down, we have that it's C1 multiplied by xi, the normal eigenvector, that is 1 minus 1 exponential of 2t, plus C2 multiplied by the whole block, that is eta, a minus 1 exponential of 2t, plus the normal eigenvector, that is 1 minus 1 t exponential of 2t. We might notice that we have a C1 multiplied by 1 minus 1 exponential of 2t, and the C2 a minus a exponential of 2t. We can take that a minus a exponential of 2t away, and now we have something a bit simpler, that is C1 multiplied by C1 tilde, a new value of C1, multiplied by 1 minus 1 exponential of 2t, plus C2 multiplied by the block, that is 0 minus 1 exponential of 2t, plus 1 minus 1t exponential of 2t. Notice how this is, every time you'll solve for generalized eigenvectors, you should be able to solve for the extra parameter that you gain. So to get it away and only have something that depends on C1 and C2. But the way in which this happens will change